We've been looking at differential equations like this one. Second derivative of y minus twice the derivative of y plus y equals 0. Now, whenever we've solved them, we've found ourselves coming up with a quadratic equation and solving that. We haven't seen what happens when there are repeated roots, and this video will explore that. So here we guess that y equals e to the kx, as usual, and then we try to find out what k must be by solving an equation. And the equation here, we get a k squared term from here, we get a minus 2k from here, and we get a plus 1 from here. So the equation we'd be trying to solve is k squared minus 2k plus 1 equals 0. Of course, this factorizes immediately by I. So we get k minus 1 times k minus 1 equals 0. And unfortunately, that has just one root, or if you like, the same root twice. So whereas normally this technique would give us two solutions, and we can add and subtract those and get a two-parameter family of solutions, when we have repeated roots, we're missing a solution. So all we get from this is y equals e to the x times a constant. We could worry that there are more solutions that we haven't found. When we're solving a second-order differential equation, we usually expect to find a two-parameter family of solutions. But here we only have one parameter, parameterized by the constant a. So what have we missed? When this happens, it turns out that it's a good idea to try multiplying your guess by x. Let's see how that works here. If we take y equals x times e to the x, then dy by dx, well, we can use the product rule to work that out. We get e to the x when we differentiate x, and we get x times e to the x when we differentiate e to the x. And so adding those together, we get x plus 1 times e to the x. And similarly, when we differentiate that again, we get x plus 2 times e to the x. Now let's substitute those into here and see if it satisfies the equation. We get d squared y by dx squared equals x plus 2 e to the x minus two lots of this two times x plus 1 e to the x plus this. Now, is this 0? We can check the x terms and the constant terms separately. We get x times e to the x minus 2x times e to the x plus x times e to the x, which is of course 0. And the constant terms, we get 2e to the x minus 2e to the x. So this is indeed 0. So we found another solution. As normal, we can add multiples of it to other solutions. So we find that our general solution is in fact not y equals a times e to the x, but y equals a to the x plus bx e to the x, which if we preferred, of course, we could write as a plus bx times e to the x. And that turns out to be the general solution. We have a two-parameter family of solutions parameterized by constants a and b. We can take any constants a and b we like, and we get a solution a plus bx times e to the x. In fact, this trick works for equations of higher order as well. Let's see an example. So we're going to consider the equation d cubed y by dx cubed minus 3 dy by dx minus 2y equals 0. Now this isn't an order 2 equation like the ones we've been considering in the last couple of videos and in the first half of this video, but it turns out that the same technique solves it just the same. If we guess that y equals e to the kx for some k, then of course dy by dx equals k e to the kx, and d2y by dx squared equals k squared e to the kx, and d cubed y by dx cubed equals k cubed e to the kx. Hence, when we substitute these into this differential equation, what we get is k cubed e to the kx minus 3k e to the kx minus 2 e to the kx equals 0. Dividing out by e to the kx as usual, we now get a cubic equation. K cubed minus 3k minus 2 equals 0. Of course, solving cubics is rather harder than solving quadratics, but in this case, it turns out we can just spot a solution. See, if we take k to be minus 1, then k cubed is minus 1, minus 3k is plus 3, and minus 2 is minus 2, so we get minus 1 plus 3 minus 2 is 0. So we know that this has one root at minus 1, and therefore a factor k plus 1. Or we can just ask ourselves what the other factor is. And we need a k squared to multiply to get the k cubed. And we need a minus 2 to multiply to get the minus 2 as the constant term. And then it's not hard to see that the factor that makes the rest of it work is minus k, as then we pick up a minus k from here and a minus 2k from here, and that gives us our linear term minus 3k. Now this quadratic we can now factorise by I. What we get is another factor of k plus 1 and a factor k minus 2 multiplying to give 0. Because k plus 1 times k minus 2 is k squared minus k minus 2. Now, that means that we can take y equals e to the 2k, e to the 2x, and that's a solution. And it means we can take y equals e to the minus x, and that's a solution. But this is a repeated root in the cubic, and it turns out that that means, as before, we should try multiplying the corresponding solution by x. But let's check it works. If we try y equals x times e to the minus x, let's check that this is also a solution. So using the product rule, we find that dy by dx is now 1 minus x e to the minus x. And we find that the second derivative of y with respect to x is x minus 2 e to the minus x. And lastly, the third derivative is equal to 3 minus x times e to the minus x. Okay, let's put all those together and check that it works. So, 3 minus x e to the minus x is d cubed y by dx cubed. Minus 3, 1 minus x e to the minus x, which is minus 3 dy by dx, plus, minus 2y, and y was x e to the minus x. What does that give us? Well, for the x e to the minus x term, we get minus x plus 3x minus 2x, which is 0. And for the constant term, we get 3 minus 3e to the minus x. So this is indeed 0. So we found another solution. So as usual, our general solution consists of linear combinations of the solutions we found. So a general solution for this is a e to the 2x plus b e to the minus x plus c x e to the minus x. Or if you prefer, a e to the 2x plus b plus cx e to the minus x. And this turns out to be the way to do equations of this sort, no matter how large the order is. You guess an exponential. That gives you a polynomial equation for what the exponent must be. You solve the polynomial equation. That gives you some solutions. And whenever you have repeated roots, you need to stick an extra x in to give you another family of solutions.